Hi there. This video will show you how to use the basic functions of the Faust programming language, such as its different operators, statements, and primitives. Faust, that stands for Functional Audio Stream, is a functional programming language specifically designed for real-time signal processing and synthesis. Faust targets high-performance signal processing applications and audio plugins for a variety of platforms and standards. For more information about what Faust is intended for, you can have a look at our video, What is Faust? And the link should be displayed now on your screen. Also, to get more precise information about Faust in general, we advise you to refer to the Faust reference available online on our website, and the link should also be displayed on the screen now. Finally, in this tutorial, we assume that Faust is correctly installed on your computer as well as all its side's programs. So, in this tutorial, we're going to use FaustWorks, which is an IDE, integrated development environment for Faust. It is a very helpful tool for Faust beginners as it displays in real time both block diagrams and C++ code from the Faust code you're writing. Also, as the compilation is always processed, you'll know very quickly if your Faust code is correct or not. Although, we have to say that this is still a very experimental program, so we can't really guarantee its stability now. Okay, so let's have a closer look to FaustWorks. So in FaustWorks, you have different frames. So this is the main frame. And in this main frames, we can see all the .dsp Faust codes that are in our working directory. So here I have two different Faust codes. I have this simple program and I have this other simple program called draft DSP. So if I click on it, then it will open the Faust code, which is here. And so as you can see, it is very simple. We can see the block diagram of this Faust code, and we can also see the corresponding C++ code generated by Faust here on the right frame. Also, there is an error messages frame where all the error messages are displayed if your Faust code is wrong. Okay, so we can choose between different Faust code, as you can see, and when we will write the Faust code, the block diagrams will be automatically updated as the C++ code. As in any other program, we can choose to create new files, to open new files, or to close files that are in our working frame here. Also, we can zoom in to have a closer look to the block diagrams, as you can see here. We can decide to open our block diagrams in our usual web browser. So here it is open in Safari. Okay, same thing here. You have different options. Also, you can choose to use a larger font if you don't see the Faust code or the C++ code enough, or we can zoom out on the font as well. Finally, here we can decide which architecture will be used to compile our Faust objects. So here we only have a few architecture files. We have Pure Data, Maximus P, and Core Audio Qt. And here we can choose the mode in which your program will work. So scalar, vectorial, parallel, and parallel with OpenMP. Okay. Now let's have a look to our first Faust program, which is a simple noise generator, and this is this program. So I'm gonna zoom in on it so we can see the block diagram of this program. So once again, the Faust code is here, the generated C++ code is here, and the block diagram of this Faust code is displayed here. A Faust program is essentially a list of statements. These statements can be declarations, imports, definitions, and also documentation tags, which we don't have here. And we can also have operational C++ style comments like that one here. So we have here a one line comment, but we could also have written something like that. And this is absolutely working as well, like in C++, if you want to have a comments on several lines. All right, I'm gonna go back. All right, so these programs exhibits various kinds of statements. We have two declarations here. We have one import, we have a comment, and we have a definition, which is the main definition because of process here. We won't talk about documentation statements in this tutorial. The keyword process is the equivalent of main in C and C++. Any false program to be valid must at least define process. So this is the only definition you need in a false program. So for example, if I go in the other program we've seen before, as you can see, the only definition I have in this program is process. Okay, and this is working fine, and this is compiling, as you can see here. Finally, metadata declarations are optional and typically used to document false projects. So those are metadata's declarations, and the main difference between metadata's declarations and a comment is that they will appear in the C++ code generated by Faust, as you can see here. So here we have name and we have copyright because they were declared here. Well, I'd say that a good practice is to start a false program with some standard declaration. File imports allow to import definitions from other source files. So here we'll need some definitions. This is for the noise function, which is declared in music.lib. The Faust distribution includes several libraries like music.lib, so they're already all installed on your computer, and you can find them in the architecture directory of the Faust distribution. So here we're using music.lib, but we could have used filter.lib, math.lib, effect.lib, and many others. Now let's see how definitions work in Faust. A definition associates an identifier with an expression it stands for. Definitions are essentially a convenient shortcut avoiding to type long expressions. During compilation, more precisely during the evaluation stage, identifiers are replaced by their definitions. It is therefore always equivalent to use an identifier or directly its definition. So let's have a look at it. So here I open draft.dsp, which is almost empty Faust code. And I'm gonna write a definition here. Okay, so basically what I will do is just create a simple Faust counter. Okay, so I write counter here, say equal, and this counter will add 1 to the signal resulting from this operation, like that. Okay, sorry. Yeah. And I end with a semicolon, of course, and this should be almost a valid Faust code. Yeah. Right, and now I can use it in process. Okay, great, and we can see the results display here on the screen as a block diagram. Okay, so one thing we have to say before explaining what's going on here is what is this simple operator. So the underscore. Underscore corresponds in Faust to a basic signal. So as we had before, if we just put an underscore in our process, Because underscore corresponds to a signal, it will just take an input signal and return this signal, so output this signal. So this is working. Okay, so now if I put counter back here, we can say that block diagram. So this definition is very simple, and it's not taking any input signal. So this is not a function. One thing we could have done here, as we said before, is just using this simple algorithm directly in our process, and the result is exactly the same. So if we use definition, it's only to have a more readable false code as in any other programming language. Okay. So I won't explain now what's going on here in this simple definition, but we'll talk about all these operators later on in this tutorial. Okay, so now it is important to say that multiple definitions of the same identifier are not allowed in Faust unless it is a pattern matching based definition. And we'll also see how pattern matching works later on in this tutorial. Okay, now we can have a look to function definitions. Definitions with formal parameters correspond to functions definitions. So now if we modify the code of our counter, so we'll also change the name because we will totally transform it and we'll just create an adder. Okay. So if we keep basically just the +1 and the input signal, then we get a very simple adder. So we get and we take an input signal and we add 1 to the signal and we return the result. And this is our simple false program. Another way to write it would have been with using local variable for input signals. So here, if I just put X, and if I replace the underscore signal by X, then we will get exactly the same result. Okay, so this is a function definition in Faust. So now let's talk about expressions in Faust. Despite its textual syntax, Faust is conceptually a block diagram language. Faust expressions represent DSP block diagrams and are assembled from primitive ones using various composition operations. So in Faust, we have 5 binary composition operations that are available to combine block diagrams. We have the parallel composition, the sequential composition, the split composition, the merge composition, finally the recursive composition. So basically, one can think of each of these composition operations as a particular way to connect two block diagrams. So now we're gonna detail each of them and see how this works. So first, I'm gonna zoom on draft.dsp that I have here, which is an NT Faust code. Okay, and we're gonna use it to demonstrate how this expressions work in Faust. So the first we're gonna present is the parallel composition. Okay, so I'm just gonna write it down here so you know what we're doing. So the parallel expression in Faust is symbolized by the comma character. Okay, so basically the parallel composition tells that we'll have two different parallel signals. So in the block diagrams, we will have one signal in top of the other. So as we said before, the underscore character symbolizes signals. So basically, if we have two signals, two parallel signals, then we shall see the result display on the screen here. And we have two parallel signals. So one input, one output, one input, one output. Okay, so this is the most simple thing that we can do with parallel composition, and we can use as many signals as we want. So here we're using 2 signals, but we can use 3 signals in our parallel composition, and then we had 3 signals. We can use 4 signals, and yeah, as many as we want. So in this parallel composition, we can also use definitions, of course. So for example, let's define A. A will add 1 to an input signal and return the result, output the result. And we can define B, which will add, or even let's say multiply 0.5 to its input signal and output the result. We're gonna integrate A and B in our process. So I'm gonna clear that, and I'm gonna use A and B in parallel. So here we shall see the result display on the screen. So as we can see, A is here and B is here, and they are totally parallel definitions of the other. So we're taking one input signal here and adding 1 and outputting the result, and here we're taking one input signal, multiplying this signal by 0.5 and outputting the result. So this is a parallel composition, and as we shown before, we can create even another definition, which is C, which is a division, and we're dividing the signal by 3, for example, and if we integrate this division in our process here, with a parallel composition operator, then we have 3 parallel block diagrams. So this is the most basic expression in Faust, I'd say, and this is symbolized by the comma symbol. So let's talk about now about the sequential composition. So sequential composition in Faust are creating using the column character. So basically it is used that way. So here if we put A and here if we put B, what will happen is that the output of A will be connected to the input of B. So we'll have a sequential composition. And we can see the result display here on the screen. So basically here, A is taking an input signal and the output of A is connected to B. And we can add C here to this process. And we can see the results here as well display on the screen. Okay, so A is connected to B and B is connected to C, and we have a sequential composition. So, of course, what we can do is to use Faust expressions together. So here, if we want to just write exactly the same thing, the same block of our block diagram, which is that one, A, B, C, in parallel of that one, then what we can do is just add parentheses here, and to write it again. So we can have, or even the opposite, for example. So let's connect C to B and B to A. And then the result should be displayed on the screen. And yeah, so here we have 2 parallel operations that are going on. So the first one, A connected to B and B connected to C. And the opposite one, C connected to B and B connected to A. Okay. So let's talk about now another Faust expression. And this first expression is the split expression. So the split expression is symbolized by this operator. Okay, so as you can see, this is very simple. So what's going on here is that split will take one input signal or several input signal and split all of them into different signals. So for example here, if we want to split this signal into two different signals, then we have to tell Faust that we want two signals after this one signal, and then we can see the result. So we take one signal, and the signal is split out into two different signals. Okay, so if we add another underscore character here, instead of having two different signals, we have three different signals, and four, etc., etc. So we can do whatever we want. Okay, in the same way here, if we have two input signals and we want to split them, so of course this is not working, we can do it by doing exactly the same thing. Sorry. Okay, so now what's going on is that we take two input signals, as we can see here, and these two input signals are split out, each of them into two different signals, because from two signal we want to have four signals. Sorry. Okay. So one important thing that we have to say here is that the number of inputs here has to be a multiple of the number of outputs here. Because of course, if here we just tell us that we want three signals from two signals, then the Faust compiler returns an error message. And this is normal because in that case, Faust don't know which signal will have to be split out into into two signals, and which one would just stay the same. So those number of signals and this number of signal and this number of signal in each side of the operator has to be multiple of each other. Okay, so now it works. Great. Okay, we can write some more complicated things. So let's say, for example, here that we have two different numbers in a parallel composition, which are 10 and 20. Okay, I'm gonna zoom out. So we have 10 and 20. What we want to do now is to add 10 and 20 together, multiply 10 and 20 together, and also divide 10 and 20 together, and output the result of these operations into three different outputs. Okay, so once again, we want to add them, we want to multiply them, and we want to divide them. So to do it, we're just gonna use the split operator like that, and this should work. Okay, so as we can see, 10 is added to 20, and the result of this operation is outputted. 10 is multiplied by 20, and the result of this operation is also outputted. And finally, 10 is divided by 20, and the result of this operation is outputted. Okay. And we can add another operation here, like another addition at the end, and this works as well, and we can do whatever we want from that. Okay, So if we have a split expression, a split operator in Faust, of course, we need a merge operator, which is the opposite of a split operator, of course. So you can probably guess how this operator will look like. So basically, it's just the reverse operator of splits doing it. Okay. So now what we might want to do is to merge the 4 signals from this process into one signal. So we can just tell Faust here that from the 4 different signals from here, we want to have only one signal. And then Faust will merge them all together. And it works. This is also going to work if we have an even number of signal, of course. Okay, so if we have only 3 different signals, then these 3 different signals will merge into one signal. Okay. So in the same way then for the split operator, instead of just merging them here, we can merge them into one operation. So let's say, for example, that we want to add all these 3 signals. But as we can see, this is not working. And this is because here we have an even number of signals. And because we have an even number of signals, Faust don't know how to combine the 3 different signals into one operator. So here, whether we can add 0 to tell Faust what it has to do, okay. So basically here it is just merging the results of the addition and the division all together and adding it to the multiplication, and we can use 0 wherever we want here to route the signal in the right way. Or we can just put back the operator with before, which was an addition, and then it works. All right. Okay, great. So now we're gonna talk about the last operator and the last expression that we have in Faust, which is definitely the most complex operation in terms of connections that we can do in Faust, which is the recursive operation. Okay. Okay, I'm gonna clear all what we did here. So recursive expression in Faust is symbolized by the tilde character. So here if we put A and here if we put B, we should see the result display on the screen. So basically what's going on here is that A is taking an input signal and B as well. And each of them are outputting one signal. So A will be connected to B, and the output of B will be connected to the input of A, as we can see here. And also, the output of A will split out into 2 different signals, so one going into the input of B, and one at the output of our block diagram, as we can see it here. Okay, so A take one input signal. This input signal comes from B because of the recursive composition. This signal, the output signal of A is split out into 2 different signals, one going to the input of B and one that is outputted. Okay. So with that, we can decide to do more complex things. For example, if we recall the simple program that we've seen before at the beginning of this tutorial, where we're using a noise, where we're creating a noise generator. So for this noise generator, we can see here that we have a recursive composition, which looks pretty much the same than the one we have here. So if we want to reproduce this composition in our false code here, what we can do is just replace 1 here by the value that we have here, which is 345. Okay, great. And we can replace the value that we have here as well, which then is 11,035,15245. Okay. And now we have exactly the same thing here, or not exactly, actually, pretty much the same thing, because as we can see here, all these operations were used in the same definition, which is random, which is not the case here, because we have one definition for this operation, which is B, and one definition for this operation, which is A. So what we can do is just to use these operations directly in our process here, replacing the definition in the process, and then we will have exactly the same block diagram than the one we have in this area. So we won't detail now what's going on here in terms of digital signal processing, but if you want to learn how to build a noise generator in the Faust programming language, you can have a look at the tutorial, the video tutorial, and the address of this video tutorial is displayed on the screen now. Okay, so now let's talk about iterations in Faust. Iterations are analogous to for loops in C++ and provide a convenient way to automate some complex block diagram constructions. So in Faust, we have 4 different kinds of iteration constructions, and I'm gonna show them to you now. Okay. So the most basic one is the parallel constructions with a certain number of iteration, and for that we're gonna use the par primitive, which is that one. Okay, so this function takes 3 inputs arguments. So the first one is a variable name for a counter. The second one is the number of iteration. And finally, the third one is the expression that we want to iterate several times. So for example, in that case, we can just, let's say that we want to multiply a number by 2, or multiply a signal by 2. So let's see the results. So as we can see, we have 4 iterations of this operation. So 1, 2, 3, 4. What about I here? So I is basically just recording the number of each iteration. So basically, for example, if we replace 2 here by I, then we'll get the following thing. So we can see what kind of number is saved in I. So we can say that in the first iteration, I is equal to 0. In the second iteration, it is equal to 1, and etc., etc. So I can be used within the operation in each iterations to design some things. Okay, and we'll see later that it is a very helpful tool when we want to build pattern matching system with several iterations. So if we have the parallel construction, we also have the sequential construction, of course, as we've seen before. So in that case, the output of each iteration will be connected to the input of the next iteration. So we can say that we have still 4 iterations of our expression. So here, 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 and here. And they are all connected sequentially together. Another iteration in Faust will be the sum iteration. So in that case, the result of the first iteration will be added to the result of the second iteration, and this result will be added to the result of the third iteration, and etc. and etc. So we have, in that case, 4 different inputs, like in the parallel composition, and we only have 1 output. And finally, the last kind of iterations we can use in Faust is the product iteration. And in that case, instead of adding each iteration with each other, with the result of the previous iteration, then we multiply the result of the previous iteration with the result of the current iteration, and etc. and etc. Okay, so here we have 4 iterations, but if I change this number to 6, we'll see that the block diagram will be automatically updated. So this is a very powerful tool and very useful tool that will be used quite often in Faust, and especially once again with pattern matching, as we'll see later in this tutorial. Now let's talk about numerical expressions in Faust. Numerical expressions are essentially syntactic sugar, allowing to use a familiar infix notation to express mathematical expression. So we have 3 different kinds of mathematical expression, of numerical expression, in Faust. So we have math expressions, we have bitwise expressions, and we have comparison. So first, let's detail the mathematical expressions. So they're pretty much the same that the one we can find in C++. So we can add signals together or things together. Well, basically everything is signal in Faust, so this is what we want to say. So as you can see here, we're adding 2 signals together, and we're outputting the result of this addition. We can subtract signal in Faust as well. As you can see, we can multiply signals. We can divide signals. We can also use a modulo operation. And finally, we have syntactic sugar for exponent operation, as you will see. And here we can say the syntactic sugar because this character is directly replaced in the block diagram by the power f expression, which is an expression which looks like a lot the math.h expression from C++. Okay, so after math expression, we have bitwise expressions. They're also pretty much the same than in C++. We have the OR bitwise operator. We have the AND operator. We have the XOR operator. Okay, and we also have the change of bit position to the right or to the left. So the result of that kind of operation will be a bit result. So now the last kind of numerical expressions we have the first are a comparison. So we can compare a signal to another to say if it is smaller than the second signal or if it is bigger. If it is bigger or equal, and if it is smaller or equal. Okay, we can also compare two signals to see they are equals. And finally, if they are different. The results of that kind of operation is exactly the same than in C++. So if the results of the comparison is true, then the number 1 will be outputted from this block. And if the result of the comparison is wrong, then 0 will be outputted. Okay, now let's talk about time expressions in Faust. Time expressions are used to express delay. We have two different time expression in Faust to express delay. So the most basic one is the apostrophe expression. So here we have one input signal, and this input signal will be delayed by one sample. If we add another apostrophe here, then our input signal will be delayed by 2 samples. So this is not a very convenient way if we want to have very long delay in a Faust program. So if we want to have longer delay and if we want to change in real time the size of our delay length, then we'll have to use the at operator. And after we just tell the at operator the number of samples by which the signal will be delayed. So let's say, for example, here 10. So in that case, the input signal will be delayed by 10 samples, and the result of this delay will be outputted. So as we said before, this number doesn't have to be fixed. We can change the value of this number while the program is executing. So we can use variable to control the delay length. The only thing is that we have to make sure that this value will be bounded and also that it will be a positive value. So for more information about building echo or a delay effect in Faust, we advise you to have a look at our tutorial on how to build a stereo feedback delay effect in Faust. So you shall see the link displayed on the screen now. Now let's talk about environment expressions. We have a different kind of environment expressions in Faust, and we're going to detail them now. So the first one is the with constriction, and it allows to specify a local environment. So that's what we're going to show now. So in this Faust code, I'm going to create a new definition. And this definition will be just a simple function, which is an adder, which will take one input signal and add value contained in A to this signal. All right, so if I try to compile it and if I try to add the adder to process, then the compilation won't work and we get an error message, and we can see here that the Faust compiler is complaining because A is not declared anywhere in our Faust code. So if I only use A in adder, maybe I will want just to create it as a local variable of A. Then I will use the with environment. So I use with, I open a curly bracket, and I close this curly bracket. As you can see, the semicolon has moved till the end, and we don't have semicolon anymore here. So it is like everything was on the same line. So here I'm gonna define a, and I will store a value in a. Let's say that I will store 2, and now this should work. You don't have to forget the semicolon at the end of this declaration, otherwise it won't work. So a is here. We can see that 2 was the value stored in a, and our adder is working correctly as it should. Okay, so this is the with environment, and in this environment I can also create local functions. So let's say that here I'll create a function called for multiplier, and this function will take an input signal and multiply it by 4. Okay. All right, so compilation is working fine, and here I will connect the output of this operation to mult, and we shall see the result display here on the screen. So this is working fine. So here I have the first operation, which is a plus the input signal, and here I have mult, which has been integrated correctly in our block diagram. Okay. So another environment expression is environment. And environment allows to create an explicit environment. It is like with, so what we have here, but without the left-hand expression. So it is like with, but without that. It is a convenient way to group together related definitions, to isolate groups of definitions, and also to create a namespace hierarchy. So how environment is working. So now I'm going to create a new definition, and this definition will be called constant. Okay. So in this definition, I will create an environment using the environment expression, okay? Then I open the curly bracket, I close it, and I don't forget the semicolon at the end. And in this environment, I'm gonna add some variables. So one variable could be p, and then p will be equal to 3.14. I don't forget the semicolon here as well, and e will be equal to 2.718. Okay, and I don't forget the semicolon as well here. So apparently everything is working. Now I'm gonna use one of this variable contained in the constant environment within my process. So one thing that I might want to do here is to add to the result of adder p, which is stored in constant. Then I will call the constant environment, and then p just with a dot between those two things. And as we can see, this is working perfectly. Okay, great. And also you can notice that this is exactly like in C++. All right, another environment expression in Faust is libraries import. So we can import libraries in Faust. So the library construct allows to create an environment by reading the definitions from a file. So we can have a file where many functions or variables are declared, and we can import all of them in our Faustcon just using import. Okay. Oh, I have a font size problem here. Okay, I'm gonna resume again. And I'm gonna import one of the included library in the Faust distribution, which is math.lib. Okay, I wait for compilation. So the first code is okay. So now I can use all the function definition and also all the variable definitions that are in math.lib here in my first code. So one of them is sign h, for example. So I'm gonna use it here in my process. So sign h is a function which is defined here in math.lib, and we can see that it works. However, if I disable this line with import library, we can see that it is not working anymore. And the FOSS compiler is complaining because he doesn't know the function sign h. Okay, so all right, this is compiling fine and working fine. All right, I talked about variables declared in some libraries. So one of the most important variable declared in math.lib is the SR variable, which corresponds to sampling rate. So if I use this variable like that here in my first code, then the sampling rate used by the system when the first object will be used will be stored in this variable, and then we could use it to create our digital signal processor. One last thing about the libraries in FAUST is that, as we said before, many libraries are included in the FAUST distribution, and all these libraries contain wonderful functions that are predefined for you. And in another tutorial, you can see the address display on the screen now. We'll show you how to use these functions, and we'll detail some of them that are very nice. Okay, the last kind of environment expression in FAUST is the component expression. So component construction allows to reuse a full FAUST program as a simple expression. Okay, so how do we do that? Here we're gonna reuse this FAUST program, which is called faustprogram.dsp, that we showed at the beginning of this tutorial, and we're gonna reuse it here in this FAUST code. So what I'm gonna do is that I'm gonna clear that. Okay, and then I'm gonna call the component operator, and then I will use FAUST program.dsp. And this is working. We can say that we have exactly the same thing in our new program than in the previous program, which is stored in FAUST program.dsp. Okay, if FAUST program.dsp had an input signal, then we would have an input signal here as well. Two input signal here, two input signal as well in our new FAUST code. One last thing about the component environment expression is that we can redefine functions or variables that are already defined in the code program from the DSP file. To do it, we use square bracket, okay? And here, what I'm gonna do is that I'm gonna redefine ran max. So I just redefine ran max here, and I give it a new value, for example, 1. I add the semicolon, and now we can see that the value of ranmax has changed. So we just redefine the value of ranmax. So this is a very helpful tool when you are using the component environment expression. Okay, let's talk now about foreign function expressions. Reference to external C functions, variables, and constants can be introduced using the foreign function mechanism. An external C function is declared by indicating its name and signature as well as the required include file. So, for example, in this Faust code, we want to use a function which is declared in math.h, which is a C function. Okay, so the function we want to use here is a sin h. Okay, so I will define a new Faust function here. So a sin h is defined in Faust. Now I'm gonna use the foreign function mechanism to call it and to import it from math.h. So the first thing we need to do is to tell the foreign function mechanism which function we want to import. So actually this is a sin h. Then we have to indicate to Faust the signature of this function. So this function will return a float number and takes a float number as an input. So we have to tell Faust all these things. Okay, all right, so here we have math.h, and the last thing we have to do now is to introduce a comment for this function, but we don't want to write anything here. So as we can see, the Faust code is okay. And now we can use the a sin h function, which is a C++ function, directly in our Faust code. And as we can see, this is working. Okay, we can do exactly the same thing with constant and variable. Then instead of using foreign function, we will use the keywords, which are f constant or f variable. F variable. Okay, I don't want to show you now how they work because this is exactly the same thing than here. Okay, so we introduced here the signature of a function, so the type of the numbers that are used in a function. Basically, in Faust, we only have two types, which are float numbers or integers, and that's all we need. So let's say that now I have a float number, and this float number will be, for example, 5.45896. Okay. Yeah, I want to use this number in my process. So if I want to cast this number so it will become an integer, I will just have to do that. Okay, so as we can see, this number will be converted to an integer. So more logical thing will be just to write something like that. So here we have a float number, and this float number will be converted as an integer. Another way to do it will have been to write it in the C++ way. So this is the Faust way, using the sequential connection operator. But we could also have used the old-fashioned C++ way to write it, which is something like that. And then we can see that we got exactly the same results. Okay, we can do exactly the other thing. So let's say that here we have 5, which is an integer, and we want to convert it as a float number. Then we can just do that. Generally in Faust, it's not really a big deal if you only use float numbers because the compiler will optimize the code, so you won't have any cast problems in your final C++ code. Okay, now let's talk about the pattern matching facility from Faust. Formal parameters of a function can also be full expressions representing patterns. This mechanism allows to algorithmically create and manipulate block diagrams expressions. Okay, so here in our false code, let's say that we want to declare a new variable, and this and we'll store a number in this variable, and the number we're going to store is 0.1. Okay. So now we want to use this variable in our process, and of course this works, and the number is stored in P is outputted. Okay, now we will declare one more time P, and we'll store a new value in P, which is 0, and then of course we got probably some problems and troubles because we'll have different values stored in the same variable, which is not possible. Okay, so now we're gonna store a new value in P. Okay, so what we want to do now is to output those three values at the same time in our process. To do it, we're going to use the pattern matching system. So here, we're going to use arguments for each of our functions, but instead of putting argument name, we're going to use numbers. So here we're going to use 1, here is 0, here 1, and here we're going to use 2. So this is still not working because process don't know which of them it has to use. So here, if we use 1, then the value that is stored in P0 will be outputted, and so it is 0.1. If we use P1, then the value stored in P1 will be outputted, so it is 0, etc. So to output these three values in a sequential composition, we're gonna use the sequential iteration system from Faust. So I'm gonna declare counter name, which is I, and we want to have three iterations. So actually we don't want a sequential composition, but a parallel composition. We want a 3 iteration of P. Okay, and now instead of 1, I'm gonna use I here, and then we got the 3 different values we wanted to have outputted all together at the same time in a parallel composition. Okay, so this is a very useful tool, and we're going to show you why. So, for example, let's say that we want to build a filter bank, a very simple, very basic filter bank. So now I'm going to import the filter.lib library, which is part of the Faust distribution. So I call filter.lib. And actually, it is filters.lib. And yeah, of course, I don't have to forget the semicolon, and it is filter.lib. Okay, great. And in filter.lib, I have a one-pole filter, and the name of the function used for this one-pole filter is pole. Okay. So here I'm gonna clear that, and I'm gonna call the pole function. All right, so now what I want to do is to use the values stored in the 3 different values stored in P as a pole for my one-pole filter. So now what I'm gonna do is to use P and put I again in it. Then I will have 3 one-pole filter that are used in my process, and they're all in parallel. So I said that I want to filter banks. So actually, I want to have one input signal. So I will use the split composition here to take one input signal and to split it out into 3 different signals and to send these signals to my filter bank. And at the end, I will merge the 3 signals outputted by my 3 one-pole filter into one signal. And now I have a filter bank made of one-pole filter. Okay, so one last thing about pattern matching. Now, let's say that we want to describe a function to duplicate an expression several times in parallel. So basically, doing pretty much the same thing than the parallel composition system that we're using here in Faust. Okay. So I will clear all that. I will declare process another time here. Okay, and I will define a function which is called duplicate. Okay. This function will have a pattern matching system here and also an input signal which is x. Okay. So this should work, great, okay. So here, if I use duplicate and if I just recall 1, because this is the first version of duplicate, then basically I just take an input signal and I return this input signal. Okay, so PM stands for pattern matching here. Okay, now I'm gonna reuse duplicate here, okay, and instead of 1, I will put a variable which is n, and I still take the input signal which is x. Then I'm gonna put x here, create a parallel composition, and then recall duplicate from the previous declaration, and then I will do n minus 1 and still x here. So we still have exactly the same results, but a different thing now is that, for example, if I use 2 here, then our input signal will be duplicated into 2 different signals. Okay, so basically what we did here is that we created a kind of loop and a kind of for loop, and basically we just define the number of iteration we want just using pattern matching. Okay, so here if I put 4, then my input signal, which is stored in x, will be duplicated into 4 different signals. Now let's talk about primitives in Faust. We won't detail all the primitives that you can find in the Faust programming language because that will be too long. But if you wish to have more exhaustive list of them, then we advise you to have a look to the Faust manual that is available online on our website, and the link shall be displayed on your screen now. Okay, let's just talk a bit about the delay and table primitives. So before we said that to create a delay to a signal, we can just use an apostrophe, so we'll create one sample delay. Or if we want to create a longer delay, then we can use the add operator, and then we define the length of our delay line in number of sample. And in that case, the input signal here will be delayed by 10 samples. But there are also actually some more complicated way to create delay lines in Faust. We won't detail them here, but just to tell you, we have 2 other operators, which are the read table operator and also the read and write table operator that can be used to create more complicated and more efficient delay lines. There is a tutorial about it, and the link should be also displayed on your screen now. So if you want to learn more about that kind of thing, we advise you to have a look at it. Okay, another thing, another kind of primitive we have in Faust and that we didn't talk about yet are the selectors. We have two different selectors in Faust. We have select 2 and we have select 3. Basically, select 2 is taking 3 signal as input. So the first signal is basically just a number which will be 0 or 1. If the first signal is 0, then the first signal here, so the second signal in select 2 will be outputted. Instead of using 0, if we use 1, then the third signal, so the second signal from the two audio signals that we're using here, will be outputted. Okay, and exactly in the same way, if we use select 3, then we'll have 4 different signals. The first signal will be the selector, and the 3 other signal will be the signal that will have to be chosen. Sorry. So 0 for the first signal, 1 for the second signal, and 3 for the third signal. Okay, one last thing we have to talk about before jumping to compilation in Faust, and the last thing you need to know to create a correct DSP code are the user interface elements. Faust user interface widgets allow an abstract description of the user interface from within the Faust code. This description is independent from any graphical user interface toolkits. So it is based on buttons, checkboxes, sliders, and also other things that are grouped together using appropriate grouping schemes. As any other Faust elements, these graphical user interface elements produce signals. So it can be combined with any other audio signal. So once again, in Faust, everything is a signal. Even this number here, 1, is just a signal because at every sample, basically, we'll just have a signal, and for every sample, we'll have 1. Okay, here as well, we won't detail all the graphical user interface elements because they are already detailed in the online manual that you can find on our website. However, I would just show you how most of them work. Okay, so let's say that we want to create a very simple one-voice mixer. So basically what we want to do is take an input signal and multiply it by a value between 0 and 1. So we'll have a mixer. So here my Faust code is invalid because amp is not defined anywhere in my Faust code. So I'm gonna define it here, and instead of putting a static value, I will use a user interface element here. So we have different user interface elements in Faust. We have sliders that can be whether horizontal or vertical. So to use an horizontal slider, we can just type H slider, which is the primitive for a horizontal slider. And we could have used here as well a vertical slider, as well as an entry primitive. So in that case, we wouldn't have any slider in the graphical user interface, but rather a number box where you can directly choose the number of amplitude. Okay. So let's say that here we're going to use an horizontal slider. The first thing we have to tell, so the first argument for each slider is a string that will name the slider in the graphical user interface. Also, if you decide to compile your object as a max MSP or a Pure plugin, that will correspond to the address where you'll have to find the value for one specific parameter. So let's call it just amplitude here. Okay, so in the graphical user interface, the name of the slider will be amplitude. The next argument of each slider is the default value of the slider. So here we're going to use 0, so the default value will just cut the signal. The next argument is the minimum value of the slider. After we have the maximum value, and finally the last argument for a slider is the step of the slider. So we can use here, for example, 0.01. So it will be a very precise slider. So we can see the result here on the screen. So nothing very special in the block diagram, but in the graphical user interface, we'll have an H slider. If we decide to compile this first code as JackQt application, for example, or JackGTK, or any standalone application with Faust. All right. So if I change the H with a V, then you can see that it's working as well, and then we will have a vertical slider. We can also have checkboxes, buttons, and things like that. So in the case of checkboxes, instead of having the choice between different values for, well, more like a range of value for one definition, then we will just choose between two different values, which will be actually 0 or 1. So for example, if I want to put a mute button here in my simple slider, I could use a checkbox primitive as an input for the graphical user interface, and then I would just have to name it with a string. So let's just say that this is a mute button, and then I can just add mute here to my algorithm, and then okay, that compilation should work. So in that case, when the mute button is when the mute checkbox is checked, then the signal is let pass through. But if it is unchecked, then the signal is cut off. So that's not really what we want. So we can just reverse the result of this checkbox just by putting a 1 and a minus here. So in that case, that will be a true mute button. Okay. In those graphical user or in those user interface elements, we might want to use metadata to be more specific about the graphical user interface. So here, instead of using a vertical slider, we might want to use knobs. So in that case, I'm going to use a metadata. So metadata are declared in the string with square brackets. And here I will just change the style of the slider, and I will tell Faust that I want a knob instead of a slider. So all the metadata types are also detailed in the manual of Faust available online on our website. This could also have been, for example, a unit. So here we have amplitude. So let's just say that the amplitude would have been in decibels. So it is not the case here, but just suppose that it was in decibels, and then we'll have the decibel unit displayed as well on the graphical user interface. We also have some system in Faust that will make it possible to create a hierarchy inside our Faust signal processor, and that will be displayed afterward in the graphical user interface using the H group or the V group primitive. But we won't detail that here because this is already done in the online manual. So if you want to learn more about it, we advise you one more time to have a look to the Faust online manual.